Thank you for the presentation. I'm Sergio Arrieta from the University of Cantabria, and I'm going to present our work entitled Estimation of Fracture Loads in 3D printed plant notch specimen using average strain energy density criterion. Well, this is the structure of the presentation. At the beginning, I'm going to do an introduction. Later, I'm going to explain the methodology that we used. Later, I'm going to speak about the material that we are using and showing the result, and finally some conclusions. Well, as you know, notches produce a stress concentration which leads to the brittle fracture. In this case, we are using the average strain energy density as value criterion. In this research, we applied this methodology to estimate the fracture loads of 3D printed polyacid plates containing U notches. Well, this is the methodology that we are using, is the average strain energy density, and following this criterion, the failures of blue occurs if the average value of elastic strain energy, if the failures occur if the average value of elastic strain energy within a certain area is equal to a critical value. The control volume around the notch tip is characterized by the critical radius following these equations. Well, the average strain energy in the control volume is defined by the following equation. It depends on the maximum elastic stress at notch tip, the Young modulus, and two parameters which depends of the notch geometry and the Poisson ratio. Applying ASED criterion to the fracture behavior on the 3D printed plates, we estimate which is the critical value from tensile properties. Combining both equations, we obtain the maximum elastic stress at notch tip. Later, we use a Kager-Parry equation to estimate the external loads which causes the maximum stress at a notch tip. And finally, we estimate the stress intensity factor for calculating the critical loading. This equation is the one that it should be used for a single edge notch specimen. From a previous work, we have the characterization of the material. And we already know all the mechanical properties for this plant material. These are the specimens that we are now using to estimate the critical loads. They are 3D printed PLA with the orientation of 45 degrees. We have performed 27 fracture tests with 2 different notch radius and 3 different thickness, and 2 different radius between the notch length and the width of the specimen. Well, this is a picture of the setup and some of the displacement versus the load versus displacement curve that we have found in different specimens. The first estimation using the ASED criterion give us some really low prediction for loading. So we applied this calibration. As ASED was validated for linear elastic behavior and PLA is a non-linear material, we made this calibration using the same specimen that we had from this previous work. With these 2 calibration curves, we obtained the ASED parameters. A new average strain energy in the control volume and a new critical radius at the notch tip. Applying this new value, we improve the prediction of the loads. So in this case, we increase our 50% of the improvement of 50% of the predictions. And now to conclude, Well, we have used the ASED criterion to 3D printed PLA using with no U-notch and different combination of notch length and width. Using directly the ASED criterion, we found excessively conservative critical loads, but applying this calibration, we improved the load prediction, and they are, although they are still conservative, but we are now in reasonable safety margin that is between 1.3 and 2. So thank you for your attention, and if you have any questions.